Hi, everybody. I hope to speak with enough energy. So my presentation is about making user space aware of deadline current instantaneous parameters. I'm an associate professor at the Real-Time Systems Lab, which is the same university where Yuri got a PhD, just in case. Just recently associated also with Merritt Dallens University for doing a collaboration, but this is just background information. So actually, as I mentioned to some of you, what I'm going to explain in the presentation is a bit longer than the patch itself. It would have been faster just to show the patch on the screen. I'm just going through the motivations. So in classical real-time tasks, real-time processing tasks, we have this sort of periodic or sporadic tasks where you should know what is the worst case execution time of your task and what is the minimum activation periodicity of your task. And the way you normally address this, and you can use deadline to schedule this task, is to run it under deadline using a runtime that is greater than the worst case execution time of your task, and also using a deadline equals period that is lower than the minimum interarrival period of your task. This basically makes sure that every time this task is activated, all right, there is a little bit other catches. So you need to partition your platform because global EDF doesn't really guarantee you much. But so if you do the things properly, you make sure that every time your task is activated, the kernel guarantees you your runtime on the CPU by the deadline, which is what you need to make sure you don't miss your deadline. Basic stuff. On the right, we can see a little bit more adaptive real-time task behavior that basically does the same thing as the left task, but only with an algorithm, with some type of control algorithm that can be adaptive. So the idea is that I have a mandatory part of computations I do all the times. Then there is some optional part I may do later. So the idea is that by definition, the worst case of my task, one I'm supposed to point it some way. I don't know which one is the start is the point. Yeah, this execution time is an upper bound. So it's not like I'm always getting there. Actually, it's quite unlikely that my execution time gets there. So the idea is that if I have some extra time in my period, maybe I can refine my control algorithm. The idea is that I can have a rough control algorithm in case I'm running late. If I'm on time and I have extra time, I'm going to refine the number and provide an output that is better, whatever it means. There's a number of control algorithms that can do these things. So in this case, basically, the idea is that in our code skeleton is that I execute a mandatory part of the computation, but then if I have some runtime left, and this is normally something you check not really in work clock time with the deadline. So it's not like if the deadline is farther away enough, but normally you need to check your runtime left to know what is, how far I am from being throttled eventually. So if I have enough runtime left, then I do the optional part of computations, then keep going for the next period. Okay, so how do we know what is the runtime left? Looks like quite a silly question. We can do it very simple way by using thread CPU time ID in our tasks. So we can do measurements around the first part mandatory computations and get it, and then basically do our check our condition. One problem we may have in this way is that we are doing this in a user space in a way that may be a little bit not really perfectly in sync with what the kernel is doing in kernel space. So it's like, okay, we are doing our own measurements, but are we sure really that this is well aligned with what the kernel actually has as our current runtime? Maybe our current runtime will probably be, the real runtime of the kernel will be a little bit lower than that, but we can account for that in these calculations. Okay, this is not such a big problem. However, if we really want to make sure, one way could be, okay, why don't we go reading the current runtime? We have it available in TalkPid scat, and we can read it from there. However, it's a bit inefficient. So The other motivation that we use actually in this joint paper with Lawrence University is that we might have different use cases where, for example, in this case, we have fundamentally a thread pool of tasks that for whatever reason you may want to schedule them with deadline because you want temporal isolation. You want to make sure these tasks can run, treat them as a parallel component in your system that doesn't get interference from other tasks. So in this case, we may have actually a pool of threads that pull jobs out of a queue, where each job comes with a submission time and a deadline. And the idea is that okay, if I can process one of these tasks, one of these jobs on time, I process it. But if I can't, I let it go. I'm going to skip the job. So the idea is to have a loop like this in our code. Like, I put a job, then I see if it's feasible to serve this job, given the job worst case execution time, and given, this is the best estimate I have of my job execution time, and this is the absolute deadline of the job, then I can process the job. Otherwise, some way I dismiss the job, or we can leave the job to be picked up by another thread in the pool, because we're a thread, a pool of threads, of deadline server threads, each one that is not really aligned with the other. So they may have different deadlines, they might have consumed different runtimes at any times. Okay, so here the problem comes. How do we actually check if a job is feasible? So the way we can do is simply, if we consider what deadline is guaranteeing us. So again, under proper conditions, let's say if you use deadline the right way, which normally means not really use the global EDF feature, but use it in a partitioned way. So it guarantees that we have our runtime left by the current deadline. So if you consider this picture, this is the moment where we do this evaluation. In this moment, we don't have really our full runtime. We don't know, we will probably have some consumed runtime, so we have runtime left. We have our current absolute deadline. Then there will be the next period, okay? However, what I evaluate now is this. If my job deadline is, let's say, within, on this deadline, then I have my total runtime left guaranteed, because because of course that's the guarantee of the scheduler. However, if the job deadline is a bit low, is earlier than the deadline of the server, I can still know something about guarantees by assuming the worst case. In the worst case, my runtime left will be granted at the end of the reservation period. That's my worst case evaluation. Actually, I can do a little bit better than this, and we do it in the paper, but I don't want to bore you with this stuff. So in this worst case scenario, basically, if the job deadline is a little bit earlier than the deadline, let's say by X, then I get as a guarantee runtime left minus X. This is the time available till the moment, the job deadline. So I can do my check. And what happens in case my job actually goes beyond the current deadline? Because it's not like we can guarantee anything. We can still make guarantees, because when we go beyond the deadline, our job deadline can actually be, beyond the server deadline, can be 1, 2 periods apart or whatever. So in this case, again, we know we have the runtime left, the current deadline, then we have the full runtime for every period that is in between. And for the last period, we know we have to subtract again a possible, value X from the last period absolute deadline of the server. And so this is roughly what you can do here with a few scaling operations, etc. So what I want to say is that we can have a way to make these computations of compute fundamentally what is the estimated worst case finishing time of that job, assuming the job worst case execution time is accurate. Okay, and finally, I just compare it with the job deadline. Say, if I can finish this job by its deadline, I will process it, or otherwise I won't. Now, the problem comes, okay, but in this picture, it is clear. Not only do I need the runtime left, I need also to know what is my absolute deadline in user space. And so this is something we never cared about really in SCAD deadline. So we only say, okay, we set the parameters, schedule the task. The kernel will do the magic. For user space, you don't need to do, don't need to know much else. However, yeah, in this case, we actually need to know what is the status of the deadline server. Okay, so this is a few ways we can do that. And actually, we went through all of this during this paper. But basically, we can do it with a quick and dirty user space hack, which is the bad way. Then we can do it even, with a better way, but inefficient. Then we can do it with a kernel module. We can do it the right way with a small modification to the get-TTR system call. Okay, so let's see one by one, just to understand what's the problem. So the user space hack, as I say, the runtime left is easy because we can use the thread CPU time ID. However, the absolute deadline is a real mess. But if you think about it, SCAD deadline has a nice guarantee of being self-synchronizing. So that means that if I sleep enough in user space, I do a clock nano sleep of at least a period, I'm sure that when I wake up, the deadline resets the absolute deadline to the wake up time plus 1 period. So this is a trick we can use to make sure that the notion of time we use in the user space with a clock nano sleep, the sleep still an absolute time, a point in time in the future, that this time is actually also well aligned with the SCAD deadline, absolute deadline used by the server, by the deadline scheduler. And this is actually what you can do. Okay, at the beginning of your application, nobody cares about performance, so why not sleep one instance and then keep going, and you are aligned, right? And of course, you have to rely on periodic displacements of your deadline for future periods. So, however, yeah, there's this problem that we are basically doing two open loop estimations. So one is the runtime, which actually might be lower than we think, but I mean, this is not really a big problem. A bigger problem is the one that the server deadline might reset non-periodically due to the CBS wake-up rule. So if we don't have jobs in the queue to pull at some point, we spend some more time, then we have a reset when we wake up. And again, we have the problem that we don't know how we are synchronized with the server deadline. And the other problem is that there might be more nasty, a little more nasty problem, that there might be a drift. Even if I woke up periodically, there might be a drift about my notion of time in user space, like clock monotonic, and actually the 1Q clock used in the kernel for doing, the kernel accounting. And so this is actually creating some synchronization problem. So let's say, okay, how can we do that? We can do this differently by reading actually the debugging interface. So if we go and read proc till task till SCAD, we find actually this information stored in the dl.runtime and dl.deadline lines in SCAD. Okay. However, this has two problems. So first, it's highly inefficient. As you can see here in a Raspberry Pi, this was taking like 230 microseconds plus, up to 250 and even more microseconds, because I need to parse numbers to do a lot of wasteful operations. But additionally, the deadline returned by the kernel is in 1Q clock reference, and that's what I find in the proc file system entry. So again, I don't make much use of that in user space, albeit I can still use the same hack I told you earlier to basically create at the beginning of my application a sort of offset. So I make this usual experiment. I read the deadline in 1Q clock. I just store the difference with the clock monotonic reference when I woke up, and I use it as, okay, this is the offset between the two. I'm going to use it to compute monotonic time based on 1Q clock time, etc. However, I mean, there would be one way of dealing with the situation, except that the two clocks will be drifting a little bit, that problem stays, and it's actually, so we would need to redo that from time to time to make sure we are aligned. But anyway, it's a big mess. Yeah, so there is one thing I wanted to say, so we may need to resync. And this is actually like example code that does that. Don't look at that, it's not efficient. Okay, so the other way we actually used, we tried was through a kernel module. Okay, let's write a kernel module. However, so a kernel module is easy. We just expose a device, a special device called DL params that it can be read by the user space application. We read the params, we get two long values that represent our runtime and deadline. And this is ideally what we would like to do. However, so this is the kernel module implementation. So we just copy the values we need from the deadline scheduling entity into the user space provided buffers. However, there's a catch that if we copy these parameters as they are in the kernel, the runtime would not be updated because we need to update the current runtime. So it gets only updating basically when you call the scheduler. But as we are doing a syscall, we are not calling the scheduler yet. So we will get the old runtime at the due, as updated basically at the beginning of the current time slice. Okay, from a kernel module, we don't have really any of the API of the deadline API because it's hidden in deadline C in the kernel implementation. But there is one API that is easy to use, which is schedule. We call schedule, we get it updated. So runtime will be updated. And okay, deadline will stay the same, or I get throttled, whatever. But anyway, it doesn't matter. So once I do this, I can copy the parameters to user space. However, still, what I'm copying, I might be copying a deadline that is expressed in run queue clock time, which again might be difficult, hard to read for user space, but nothing prevents me from doing this easy fix, like take the deadline, subtract the task run queue clock, and add the monotonic time, and then return it to user space. So I could even do that. So just I want to say, if you really want, like in a kernel module, you can address this problem, but okay, it's good that it uses a binary kernel space user space interface, so there's no wasteful formatting in decimal notation of the numbers from the kernel. There's no wasteful parsing of the numbers from user space. But also, the plot sched has additional overheads because I have to go through the whole whatever stays before kernel sched anyway, so before my parameters. And I can see it's much faster, like still on the Raspberry Pi, it was 10 microseconds versus 250 microseconds to do this. However, there's a problem that this cannot work so it only works from the same thread that is get deadline. So if the thread is making this call, it works. If I do this call, I execute this module from a different thread, I'm going to schedule the current thread that is querying the system, which has nothing to do with, it might be a different CPU, the wrong CPU compared to where the task is running. So actually, I will still get the state runtime information that is not updated. And so anyway, this might be one problem, plus
so also for calling schedules. And calling schedule itself is not particularly pretty.
Yeah, then whatever. It can be an overkill. This, of course, can be a totally overkill. And okay, so the thing is, okay, the right way to do this seems to be like a kernel patch to the system calls get at, which, as I said, is faster to show than all the presentation and all the text I'm speaking with. But so anyway, just we modified the get parameters. The idea here is to add one additional flag that it needs to pass to this function. And in the flag, basically, is that 0. We have a flag in the user space interface that is mandatorily set to 0. So if you look at the user space code, yeah, there is this 0. Here for now, we have in the man page, it has to be set to 0. It's unused, can be used for future extensions. And this is a possible, voila, yeah, possible future extension. So we can pass 1. That means, please give me back not really the static runtime and deadline parameters, but please give me the instantaneous leftover runtime and the absolute deadline converted into clock monotonic time, please. That is the proposal so far. So yeah, the advantage is of course the same as the kernel module basically. However, it skips. You don't need to open a special device. You skip you basically add the functionality that in SCHED-Deadline has been missing since a long time. And actually, we've been always using hacks like this in research all the time. You need a real-time task that has to do things that are a little bit adaptive, a little bit dynamic. So you need this information continuously. So. Okay, now a little bit of numbers. So, yeah, okay, or actually questions to people here. So one question is, a variant of this was using actually two possible flags in the SCHED-GetAt. One to return the time relative to monotonic. The other one was to return the time relative to real-time clock. You can use K-time.
Go to that.
Thank you. So, first question answer.
The real-time clock can be set. It can be set.
Yeah, but you can wait till it, right? You can nano-sleep, you can compare times, you can use it as a timer base, if whatever. I mean.
But if you want to, the kernel, the scheduler can use it. So the scheduler has always to be on monotonic.
Yeah, just, multimedia applications, sometimes there's a need because different platforms, different nodes, they have.
Yeah, sure. But
so, they use absolute time steps. I mean, a classical media applications, video player uses a time step in the frames. The time step is an absolute time that is compared in world clock time. It's not used for, as it goes over a network, it's not used for in monotonic time locally. So normally in a video player that does streaming, you often need this continuous comparison with world clock time. Anyway, I assume there's no one like changing the time zone continuously or, I don't know, rolling the watch, the clock back and forth.
Then you just, the user space could do the conversion. I mean,
you can also leave the function user space.
the user space gets, if it's doing synchronization with real time clock.
Yeah, this came simply out because when we looked at this in the end, at this part of the text that
By the way, I can never read with dark mode on slides.
Yeah, that's really bad. Sorry about it. So I can't even find whatever I wanted to find. it was basically this. Yeah, whenever because we are, removing vacuum clock and we adding back K-time to an S, but as there are four functions, there's K-time to an S and K-time monotonic, there's K-time whatever else. So just, okay, maybe the real time is, but yeah, there was one question we had. So another question, we have a reading that is not really constant, albeit conceptually speaking, on a deadline task during the same period, if I read this number over and over again, it should be a constant. So you see, it's a perfectly constant, right? We run a task, a deadline task. Of course, every period, the deadline goes up. But if we actually look at the detail, it's not really constant. It's dancing because when I do this re-offsetting between vacuum clock and monotonic, I have a little dancing back and forth. It's not a constant. And this is clearly visible also if you look at the numbers. But moreover, not only is not constant, but if you look at, well, it's drifting. Now, in this case, it was drifting downwards. I guess you might have also the other case that drifts a little bit upwards.
Because you're sampling twice, right? You're sampling twice. When you read the monotonic time, like the Runke clock time that you read, there's time in between those two reads, right? And so that's probably what that variance is from.
Yeah, the variance, yes, but the drifting is, I think, is a little bit more nasty. It's probably because monotonic is getting some fix-ups of the local frequency compared to the atomic clock and TPD and whatever else. And the vacuum clock instead probably is only sticks to the current. However, I tried also to change the clock source, as you mentioned. A couple, I think I had only HPAT and TSC on this platform. I kept seeing this drift, but
there's also the monotonic raw clock, and that is a monotonic clock that is non-NTP adjusted.
Yeah, the monotonic row is, if you try to use it for user space, the problem is, if I remember well, is that you can't really sleep. You can't use it with a timer, right? So normally, I don't know, I tried a few times to use it, and as I couldn't sleep, then
no, you can't.
so I don't know if there's a good reason for that. You know probably better. So anyway, there's this little drift that you will read from user space. So we thought with Yuri, okay, we could cheat and cache the value and return a constant value so that we make the user not complain about this always changing and dancing number. By the way, we're talking about tenths of nanosecond range. This is tenths of nanosecond range, okay? But then there is this little drift. But still, it's over a task period that hopefully will be like a few milliseconds or maybe 100 milliseconds. Even make it a second, it does make a difference. This drift will be anyway a bunch of nanoseconds with 50, 100 nanoseconds. But still, it's something that may be disturbing for the user in the end. That calls twice a function, expects to see the same value, and sees a different value. So I don't know. One possibility could be to use a caching mechanism. Other questions or doubts were that this reading of the deadline parameters is actually affecting the behavior of the scheduler. We could claim in a good sense, but so SK deadline normally throttles task on the next hertz tick, right? So if you update the deadline parameters, you get throttled immediately as you read a negative value, you are throttled right away.
But there is also the HRT feature. So when you want to be more precise, we actually throttle the exact instant the time you deplete your time. So this thing can actually be thought as going to that direction. So it probably is not such a bad thing.
Okay, so with the high resolution,
it might be adding, of course, overhead if you constantly read that thing, because you're redoing the updates every time.
Yeah, and then the final is if this code is safe, basically to be called from a different CPU than the one of the scheduling task is running. We don't really have a use case for that, but if you have a syscall, it's better if it works under any condition, doing the right thing. And for us, the only things we are doing really is this, take the spin lock on the rank lock, update rank clock, and update current deadline parameters, and then release it. So the question is if this is the right thing to do from a different CPU than the rank we are talking with. We are expecting here to read the parameters. So I'm finishing this with more questions than anything else, but just in case.
One thing I was curious of, so I think you excluded kind of dynamic frequency early on in the...
Dynamic frequencies, I think in these experiments I try to keep it...
simple, constant. But I was curious if Peter's scaled monotonic time would be better to use for the CPU time, basically, where you're asking about for the thread CPU time. That scaled version would be...
The monotonic row, or?
Just because the idea of the amount of work that you have.
In case you have frequency switching.
Yeah,
the scaled monotonic. Yeah, I don't know, when it's coming, we start, of course, making good use of that. So.
But the runtime itself is actually scaled, considering the frequency. So that the runtime in kernel, the runtime is actually already scaled. So I'm not sure if we consider that. Right. Maybe we didn't.
Right now, it was taking the thread time and adding it to monotonic. So that's going to be just assuming it's.
Yeah. So maybe that thing maybe doesn't consider the fact that we actually are scaling the runtime.
Yeah, in this case, I'm really assuming I'm going constant frequency.
Yeah. So
that's all right.
Because otherwise, these calculations in the future, if my CPU frequency underneath is changing, would not work. So.
We probably need to.
But anyway, as the runtime is already like a normalized runtime left, so it's when you are changing CPU frequency, you are consuming it slower or more quickly, right? But the runtime left is still like
yeah.
But yeah, you might need to know how to convert it in time in case you are. Have any questions on this? looks reasonable, especially the touching the syscall interface, adding a flag.
That's what
using.
flags are for.
Okay.
Yeah.
Second flag for clock real time, not really. Don't like it.
And the update is.
I was briefly talking to Peter. So one problem with real time is that the application should be made aware or have a way to figure out whether the clock was set. There is a way, but this is really tedious via timer FD. So timer FD or my timer only cancels when the clock was set. Yeah, we built it because there was no way to detect it. So, but in this case, what we might do, implement a function in the VDSO which gives you the offset from monotonic to real time. So if you do that every time, and you store the previous offset and the new offset is different, and you know exactly that clock real time was jumped. Forward, backward, whatever. So I'm not sure if you want to do it in the kernel because how is the scheduler going to handle it if you have one task on monotonic, the other on real time, and then take into account that real time might be set?
Okay.
Real time was the funny DSP shifts and all that nonsense.
No, the kernel doesn't.
It doesn't?
No, because the kernel is UTC. But you still can set it.
You can make it.
Yeah, because the NTP demon, if the deviation from network time gets too big, it says no longer smooths, hammer, leap seconds. Every now and then. I mean, they still haven't agreed that they want to kill them, but.
Well, I think they agreed they want to kill it. They just haven't agreed on which particular way.
Yeah, they're debating whether they kill it in 30 years or in 50 years now. Contrary to clock time, which is strictly normally only set during boot, but still if your time synchronization goes out the window, at the time it's still set.
Yeah, and there was also this morning this talk about this suspend resumed, and I guess whatever it is. I mean, here we care about when the application is running. You might.
So monotonic is direct clock to you.
Okay, cool.
Yeah, and that I'm happy to expose an accessor to the offset in the VDSO.
Yeah,
don't even think about accessing VDSO data directly. It's going to break because I'm changing it willfully every 5 weeks. No, the problem is the data which is mapped for the VDSO access, which is shared between kernel and user space, is explicitly not an API, because otherwise we couldn't ever do any optimization or changes in the data structure.
So what happens when you change it? Like, do you have to tell libc to parse it?
No, the VDSO is a dynamic link library.
Yeah. So you can. So it doesn't matter then.
It's part of the kernel.
Yeah,
Right.
so there's code and data.
Yeah. So the core will match.
DSO just links it.
Yeah.
The DSO just links it, and the function signatures and the functionality obviously can change.
So
But-
when you add the field, you'll have to add a function as well to access it. So that would.
Yes.
So you're not supposed to directly access the data, right?
You can. It will break with the next kernel update.
Okay.
Yeah, I think I didn't have it in the slide. Other things we've been talking about was whether this could be done even to a BDS or something to read this whole information, maybe try to update it from user space and whatever. But Yeah, I think I,
That's
Yeah.
hard.
That's hard because we
Yeah.
design system-wide and not per task.
yeah,
And
Okay.
many architectures make it very difficult to have per task number.
okay. Yeah, so I mean, this, there was actually one last thing, which is about the interface, because we are returning a time information from, let's say, a clock monotonic time as a long. Does it suck, or is it acceptable? Because user space is used to time spec, and we are returning just a long value.
And
Is it acceptable?
And
Is it-
U64 value, please.
Yeah, U64 value, okay.
Not,
Yes.
not long, because that's only 32-bit on 32-bit machines.
Okay, yeah, got it, okay.
So the Stuxcat other is already U64. So that's good.
Okay,
Yeah, but I mean, it's not really hard to convert from a U64 to a time spec.
yeah, just I'm not sure if there's some corner case where you claim it's easy to convert, and then you have a machine that has been running for 3 years, I don't know.
Yes.
Okay, Okay,
I
then-
mean, most user space should use time spec 64 now. If it's not, it's going to fail in a couple of years.
okay, thank you, that's
Thank
all.
you.